All right, welcome back. So next up is the quotient rule, which, as the name suggests, is going to govern the relationship between the derivative of two quotients, two things dividing. So our f of x is defined as g of x over h of x. So f prime is going to be g prime h minus gh prime over h of x squared. Now, because the numerator is subtracting, the order is going to matter. So we have to recognize it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Another way that can help us is if we think of g of x, the top, as our high, and our h of x, the bottom, as our low, our derivative is going to be low d high minus high d low all over low low. So what it's saying is we're saying low d high, we're saying the bottom times the derivative of the top. D high means derivative of the top. High d low means the top times the derivative of the bottom over low low is the bottom squared. So low d high minus high d low over low low. It's almost like, again, sing-song kind of quality to it. It flows, so it's kind of easy to remember. Whether you remember the more algebraic means or that little trick there, it doesn't matter. You need to make sure you know your quotient rule comfortable enough that you can just go right to it immediately. So dealing with our quotient rule of our polynomial functions. So when we take this, our low d high, so our low, 2x squared minus 1, d high, the derivative of the top is 8, minus high, derivative of the top, leaving the top alone is 8x, d low, derivative of the bottom is 4x. All over low low, all over the bottom squared. Now, unlike the product rule, we are going to go ahead and distribute and combine the numerator here because there's no other version of taking this. There's no like foiling like we could have done for the product rule. We don't have that same kind of thing here. So we go ahead and distribute. We'll get a 16x squared minus 8 minus 32x squared up top. Let's FOIL out the bottom. So we'll get 4x to the fourth minus 4x squared plus 1. And then we combine the numerators up top terms, we'll get negative 16x squared minus 8 all over 4x to the fourth minus 4x squared plus 1. And that's our final answer. Again, when we get into the non-polynomial derivatives in Unit 3, we'll take a look at some examples of quotient involving those. But right now, everything is polynomial based, so it's just going to be a simple distributing and foiling process to get to your answers. All right, let's do another one. So let's say we have this one, x squared minus 1 over 5x plus 3. So we go ahead and take our derivative. So it's our low, 5x plus 3, d high, derivative of the top is 2x, minus high, x squared minus 1, d low is 5, all over low low, the 5x plus 3 squared. So we go ahead and when we distribute the 2x, we're going to get a 10x squared plus 6x. We distribute the 5, we got to distribute to the negative 1x squared and then also this negative in front there. So we're going to get a negative 5x squared plus 5. And then when we FOIL the bottom, we'll get 25x squared plus 30x plus 9. Again, you're just writing out the expression twice and foiling it, or you're recognizing your perfect square trinomial expressions for how to FOIL out 5x plus 3 squared. Combine the tops, we'll get 5x squared plus 6x plus 5 over, again, our 25x squared plus 30x plus 9. All right, so that's our quotient rule involving our polynomial function. It's not going to get any more complicated than that, as long as you can do your basic polynomial derivatives. Now, something we can also kind of talk about this in this context is the idea of the slope of what's called a normal line. Now, what is a normal line? Well, the name is a little deceptive. The normal line is a special type of line. This is a line that is, it's perpendicular to the tangent line. So, and mathematics is annoying like this. They'll give all sorts of like deceptive names. Like I'm sure you remember back in geometry, talking about the idea of a regular polygon, which just seems like a normal, nothing special about a polygon. But it turns out it was a polygon that had all sides and all angles equal. Kind of annoying that they called it regular. Same thing here with normal. Why are we calling it normal when it's got a special name? Go back in time and find the mathematician and decide that. Anyway, the process is we're going to find the slope of the tangent line. I mean, we got to find our derivative at a point and then take the perpendicular slope, which we have to recognize that if our slope was 2/3, perpendicular would be a negative 3/2. And then use that to write our equation of the normal line, where we can leave it in our point slope form, or again, if it's a nice enough problem, we can put it into slope intercepts. All right, so we want to write the equation of our normal line here. So we're given f of x is 3x squared minus 2 over 4x squared plus 1. So we have to take our derivative. So that's our low, 4x squared plus 1, d high, which is going to be 6x, minus high, 3x squared minus 2, d low, which is 8x, all over low, which is 4x squared plus 1 squared. Now, we certainly could plug the negative 1 into this point right here. However, there's a lot of different x terms in the numerator, so I want to go ahead and distribute and combine that as best I can before I substitute in. I'm going to leave the bottom as a squared expression. That'll be easier to substitute into, but the top I kind of have to simplify a little bit. So we get 24x cubed plus 6x minus 24x cubed plus 16x all over our 4x squared plus 1 squared. You'll notice the 24x cubes are going to cancel each other. In fact, that's actually going to happen a fair amount of times with these quotient rules if you happen to have the same exponent in the numerator and denominator in terms of the highest power. So see we have 3x squared and 4x squared. They're both binomials. If that case kind of holds, same exponents, both the same type binomial, you're going to find a lot of terms are going to cancel, which makes the problem a little bit easier. So now we go ahead and substitute the negative 1 into that. So our f prime at negative 1 would be 22 times negative 1 over 4 times negative 1 squared plus 1 squared. We get a negative 22 over 25. Because negative 1 squared is 1, times 4 is 4, plus 1 is 5. 5 squared is 25. So that's our slope of our tangent line. Now for our normal line, would be the negative reciprocal, so it would be 25 over 22. Now we also need the y value, so we have to substitute that back into the original. I'm going to do a different color kind of off in the top corner over here. Kind of ran out of room, didn't think carefully with that. So y is going to equal 3 times negative 1 squared minus 2, or 4 times negative 1 squared plus 1. We get 3 minus 2, or 4 plus 1, which is 1/5. So our slope for the normal line is 25 over 22. Our point is negative 1 comma 1/5. So our point slope form would be y minus 1/5 equals 25 over 22 times x plus 1. And this is a perfect candidate for why we leave it in point slope form rather than trying to distribute and put it into our y equals mx plus b. Because even though we're dealing with integers and simple rational functions, the denominators are not going to be working nice at all, so it's going to be kind of a mess to kind of distribute this and combine like terms. So this is the kind of thing that they'll leave in this format and be perfectly acceptable with that. All right, so that's the equation of a normal line, so it doesn't have to be a quotient rule to do that. This could be any type of polynomial function we've already dealt with, so basic power rule questions, could be a product rule question, any sort of question ever they ask about the normal line. Take your derivative, substitute your value, and that's your tangent slope, and then do the negative reciprocal for your perpendicular, which represents the normal slope. All right, now we don't have to be given an actual function to take a derivative. We again could use a table of values. We just apply the same rule. So h prime of x would be our low, 6g of x minus 1 d high, 6f prime, minus high, 6f of x, d low would be just g prime of x. Because derivative of 1 is 0, so it would just be the derivative of g, which is g prime. All over low, which is all over g of x minus 1 squared. Now they want all this at 0, so g of 0 is negative 2. F prime at 0 is 1/2. F of 0 is 4. And then g prime of 0 is 3/2. All divided by, again, g of 0 is negative 2, so negative 2 minus 1 squared. So if we start working through this, we get a negative 3 times 6, which is negative 18. Half of that is negative 9. And then we get a 6 times 4, which is 24, times 3/2, so half of 24 is 12, times the 3 is negative 36. And then we get negative 3 squared. So we get negative 45 over 9, which is negative 5. So h prime at 0 is negative 5. All right, so just make sure you're comfortable enough with your quotient rule that you can still apply it to given the table of values rather than actual locations, actual functions to take derivatives of. Just make sure you're matching up the correct points in the right spots. And again, as always, because the order does matter, applying the quotient rule correctly. All right, so that's it for the quotient rule. So next up is the chain rule. Last of our special types of rules regarding just regular derivatives. We'll talk about other rules again after that, as well as the non-polynomials in Unit 3. As always, thank you for watching, and I'll see you next time.